So the first goal in topic number 6 of our course is to come to grips with how to simplify expressions involving a lot of exponent arithmetic. So up here, for example, I've got a third power on an x, a fourth power on a z, and over here in a different factor, I've got a second power on x, a third power on a y, and a z over here. I've got a square happening outside of these parentheses. And then same thing down here with the addition now of some division also. Right? So if we think about what operations that we see at play in all these expressions, we actually find several different kinds of arithmetic. I'm going to go back to my little arithmetic layer cake. It's a diagram that I like to trot out every once in a while, particularly when we're talking about a new arithmetic topic. And anytime I talk about it, I talk about how I see addition as the most fundamental operation that there is in all of arithmetic. It's at the bottom of the layer cake. And its opposite, its inverse operation, is subtraction. And addition and subtraction are the foundation on which all the rest of our arithmetic is built. We don't need anything other than the basic axioms of set theory and mathematics to define what it means to add two numbers, basically. But that, in a way, we need addition to be able to define what multiplication is. And so multiplication is a layer above addition. And its inverse is division. Right? And the relationship between these two layers, one of them we've already seen. One relationship that we can see is that multiplication and division are operations that distribute over addition. And so there's a connection between these two layers. And one of the reasons that they distribute over addition and subtraction is that multiplication itself can be built out of addition as a repetition process, is repeated addition. In other words, if we have something like 4 plus 4 plus 4, the repeated addition of the same number to itself, we can rewrite that. Actually, let me write this the other way. We can rewrite that as a multiplication problem. What multiplication problem is 4 plus 4 plus 4 the same as? Four times 3, right. So one way that we can think about what multiplication means, if one of the factors in that multiplication is a positive whole number, like 3, to multiply a number by 3 means to add that number to itself 3 times. Right? 4 plus 4 plus 4 is what 4 times 3 means. So that's where this relationship comes from, and it's also the reason that multiplication distributes over addition. And so these two layers of the layer cake are where we have lived in our course so far. They're all that we need in order to completely close the book on linear equations and inequalities, which is what we spent the last 4 weeks working on. So of course, where we go next in the course is we want to go one more layer up in the cake. From multiplication to the operation which is built out of a repetition of multiplication. And that's where exponents end up coming in to the picture. If I repeat multiplication over and over again, what I get is I get exponentiation. I'm just going to write exponents here. I'll put a little caret symbol that is sometimes used to represent exponents. Like when you enter an exponential expression into WebWork, you use that little caret that's on top of the 6 on the keyboard, right? So exponents are what we get when we repeat multiplication. Again, as you were just telling me, if I multiply a number by itself 3 times, then another way to write that is to write it as that number to the power 3. Right? And given that that relationship exists, of exponents to multiplication, what do we think about a distributive property? Do exponents distribute over something? And if so, what do they distribute over? If this is the same construction as we had that linked multiplication with addition, what do exponents distribute over? So one step down, just like in the first example. Exponents distribute over the operation out of which they are built from a series of repetition. Exponents distribute over multiplication. And that's going to be one of the properties that we talk about today. Right? Because the same way in which we build multiplication out of addition, and the fact that that explains that multiplication distributes over addition, that very same fact also holds when we build exponents out of multiplication. Exponents distribute over multiplication, and therefore they also distribute over division. So this second and third layer of my cake here, this is where we're going to live for this standard. Addition and subtraction are actually going to be bit players. They're hardly going to be a part of our life for a while. We're just going to laser focus in on how multiplication and division interact with exponents for a while. Before we move away from this layer cake, though, I also want to briefly give a shout out to the inverse operation, to exponents. And to do that, I kind of want to first highlight a property that doesn't get enough exposure, which is when we talked about multiplication and addition, we said that this 4 plus 4 plus 4 could be represented as 4 times 3. Is there another multiplication problem that would also give me the same answer? It's like Jeopardy now. Give me a different multiplication problem that has this answer. Besides 4 times 3, what's another way to think about that product? 6 times 2, sure. But the 6 and the 2 are not, I don't see a 6 or a 2 here in this list. So 6 times 2 definitely has the same answer, but it seems like it originates from a very different problem. Let me ask it this way. What about 3 times 4? So from a very early age, we become accustomed to the fact that 3 times 4 is the same thing as 4 times 3. That when we memorize our times tables, whenever it is that we do that, right, there's a nice symmetry in the times tables. That in row 3, column 4 is the number 12, but it's also in row 4, column 3. Right? We're going to find 12 in those two different places. But in a way, that should still surprise us, because in the repeated addition model, 3 times 4 is not 4 plus 4 plus 4. It's 3 plus 3 plus 3 plus 3. Right? And somehow, when we look at it from the point of view of addition, it's not clear to me why these two things should be the same. But when we represent them as multiplication problems, we end up using the same two numbers, 3 and 4, just multiplying them in opposite orders. So even though they give us the same answer, they are not fundamentally the same question if we think about multiplication as a repetition of addition. This, by the way, these are the kinds of questions that people who study math education and people who go to teach math in elementary school, for example, those are the questions that elementary math teachers have to wrestle with, because the ideas underneath arithmetic are so important to people learning arithmetic for the first time, like first and second graders, for example. But if we bring that same question up to think about exponents and multiplication, is there a difference between 4 to the third power and the opposite 3 to the fourth power? What is 3 to the fourth power? If you multiply it out. Three times 3 is going to give me 9, times 3 is 27, times 3 is 81. What's 4 times 4 times 4? 4 times 4 is 16, times 4 is, uh-oh. So now we're kind of stuck. When we did this with addition and multiplication, down in this example, 3 plus 3 plus 3 plus 3 gave me 12, and so did 4 plus 4 plus 4. So whichever way we sliced it, there was the commutative property of multiplication, of which this is an illustration, tells me that multiplying works the same whichever order I do it in. But the same clearly cannot be said about exponents. It matters when I calculate an exponential expression which number is the base and which number is the exponent. If I switch the two of those around, I'm going to get a very different quantity. And so those don't necessarily have anything to do with one another, a to the b and b to the a. And for that reason, there are actually two different inverses for taking an exponent. One inverse that we'll use when our job is to discover the exponent. So I'm going to write that one up here, discover the exponent. And a different inverse that we use when the job is to discover the quantity in the base. And the names that we give to those two inverses are respectively roots, or radicals, if we feel like being really pedantic about it, and we will later on, of course. Roots and radicals are the ways that we discover the base quantity out of an exponential expression. Right? So out of these expressions, if I wanted to recover the 3 out of this, I would take the I would take the 4th root of this expression to discover the 3. So roots are how we discover the base. How we discover the exponent in an exponential expression is a whole other kettle of fish called a logarithm. So if out of this expression my job is to discover the 4, I would take a logarithm, a base 3 logarithm, in fact, to discover the 4 out of this expression. And it's the non-commutativity of the exponential operation that explains why there are 2 different ways to undo it. And unfortunately, most algebra classes situate these 2 inverses very far apart in time and space from one another. Roots tend to be something you learn in Algebra 1. Logarithms are something that you might not even see until the end of Algebra 2 if you're lucky, or pre-calculus if not that. So you will spend a lot of time in pre-calculus next semester getting well acquainted with logarithms. But my personal opinion is that because it comes so late in the math sequence, that there's still a lot of mysticism and confusion and fear about logs that I think is unwarranted. All they are their ways of reversing the exponential operation to discover the number that's in the exponent. That's all. It's a rescue tool. It's the ladder on the fire truck from which the exponent can climb down out of the expression and be recovered down at the ground level, right? So we won't get much chance to talk about logs this semester, but next semester in pre-calculus you very much will.